The good news is I think that the hardest part of Chapter 5 is over with, because starting today we hopefully will find some better ways at working some of these area underneath the curves that we've been talking about. So the title of this section is the fundamental theorem of calculus. This is what is going to link together all of our differential calculus that we did in chapters 2, chapters 3, and chapters 4. And it's going to link to this whole idea of integral calculus that we worked on in the previous video. And so there's two parts to the fundamental theorem of calculus. The first part deals with the functions defined by equation in this form. Now, what we know from this is that the area under the graph, whenever we're doing this, this integral sign right here means that we are finding the area under the graph from A to X. Okay? And so the whole idea is I still have this curve, and it's going, let's just put right here. This guy is going to be A, and we still have B happening back here at the very end. Now what this X guy is going to do is X is going to just be a random spot that is between A and B such that we can find the area from A to X. This will help us step into the second part of the fundamental theorem of calculus. But let's just practice this first part before we get going. It says if f is the function whose graph is shown in figure 2, so we have some function, have no idea what it's going to be, but it follows this blue line right here. It's probably a piecewise function with that being leveled off right there. And g of x is defined as the area from 0 to x of this function f. And the value, I want to find the values of g of 0, 1, 2, 3, 4, and 5. And then I will make a rough sketch of the graph of g. Okay, so here we go. What I'm going to do is plug in 0 in for this x. Okay? So whenever I find g of 0, well, these endpoints are going to match. It's going to be the integral from 0 to 0 of this function. Well, we know if these two numbers match, that I'm not able to get a width. I'm going from this red dot to the same red dot. There's no area there whatsoever. And so the area has to be 0. Well, that one was too easy. Let's try g of 1. So now I'm going to do the area from 0 to 1 underneath this curve. Okay, so from 0 to 1, I'm just wanting to do all this area that I have down here. Now this is going to be an estimation at best, okay? And I look at it and I do have a triangle. And so my triangle has a base of 1, it has a height of 2, so I could definitely just do 1/2 base times height, and that will give me an area of 1. That makes sense, because I could dump this little bit that's above into this vacant spot, and I would have pieced in a whole unit right there. Okay. G of 2. Now remember, whenever I say g of 2, I'm wanting to do the integral from 0 to 2 of that function. Hopefully I'm going to lose this notation just a little bit. So I still have this green shaded region I had here. So I have 1 plus, well, I have 2 more full boxes that I'm taking the area of. And so the area of this is just, if I just do length times width, it's just a 1/2, which gives me an area of 2. So my area under the curve from 0 to 2 would be equal to 3. Keep that in mind, because I can just keep progressing off this. I think you get the idea of g of 3. I'm just adding the area from 0 all the way to 3. Well, from 0 to 2, I know that area was 3. I just want to add to it this little bit of the area that's underneath the curve here. This is where we're going to have to start estimating. I'm going to go with what they had in the notes, It said that that area should be about 1.3. If you would have put 1.2, 1.5, I don't think I could count anything around 1.3 off, but we're just estimating since we had that weird shape right there. So G of 4. G of 4, I'm taking all the area that I have above the curve so far. So all of this gave me 4.3. But now I'm wanting to go down here into this area. Well, look, I'm below the axis. Anybody remember what I do whenever I'm below the axis? I subtract. I want to subtract all that area. And to me, it looks like this red area right here is the same as this whole area I'm subtracting. And so I would just subtract off 1.3. And I'm back to the number 3 on this one. Wants us to go to G of 5, so we'll go one more time. G of 5, it's going to be all my area so far. All of this that I added up. Let me switch colors so you can follow me. All this that I added up. This much that I subtracted. I'm still below the axis down here, so I still want to subtract off all of this area all the way until 5. So I'm going to take my previous answer, 3, and if I'm calling these 1.3, I'm willing to bet that this last section, I can call it 1.3 as well. So 3 minus 1.3, that'll give me 2.7. So a lot like last section, it's still the area underneath the curve. I'm subtracting it if it's below the axis right here. Let's see what, let's see how this will work with just a regular function. Okay, so I want to derive what we're going to be doing with the first part of the fundamental theorem of calculus. So suppose that I have a curve. I'm just going to make one up. You've seen that curve before. Okay. And we're going to be dealing with these intervals that go from A to B. I'm still wanting to find this area. And so the first part of the fundamental theorem says that I could just work it from A to X right here. Well, I still want to set up my approximating rectangles underneath the curve. And so I'm going to draw myself a really skinny rectangle that is H units wide. Ideally, I'll have infinitely many rectangles underneath the curve where H gets smaller and smaller and smaller and approaches 0. That makes it so the right side of this approximating rectangle is X plus H. So I'm going to go on a limb here. If I was to take the area underneath this curve all the way from this line back right here, remember, that's just my function g of x plus h. Okay, that's the area from A all the way until x plus h. But if I'm just wanting this skinny green part right here, I need to subtract off all the area going back. Oh, what color can I use? Let's go with this one. I need to subtract off all this area coming back from the left side of that approximating rectangle. Well, the area on that side, it just lines up with x right here. So it'd be minus g of x. Again, let me state what I've done, okay? So I took this whole area that was to the left, okay, all of this, including that approximating strip, and I've subtracted off the area that's just to the left of it. That should leave me with exactly the area of this approximating strip. Okay, that's what's illustrated right here, is that area. Okay. So that is, I am arguing, approximately equal to the function height of this. The function height is just my f of x. We used f of t on the last one. Times its width. So it's still equal to length times width on that. So if I do a little bit of algebra with this, I'm going to divide both sides by h. And then, remember, I'm wanting h to be as small as possible. So small that it's approaching 0. So I could end up taking the limit as h approached 0 of this function. And that should equal my function. I hope this looks familiar, because all this guy is right here is my derivative of g. Now, once again, I've kind of geeked out on this, and I've gone into way too much detail on this. So what do we need to know for the fundamental theorem of calculus? Well, part 1 says if f is continuous on AB, so there's no breaks, there's no asymptotes, anything like that, then the function g is going to be defined by g of x, which equals the integral from a to x of f of t dt. Where x is between a and b. And again, it's going to be continuous on AB, differentiable on AB, and here's the kicker right here. G prime is going to equal f of x. So let's actually plug in some functions, some numbers into this. And so the first part, it's going to ask for, the first part of fundamental theorem of calculus, it's going to be going back and asking you to find the derivative. And so if I'm wanting to do the derivative, okay, I'm going to put it in my f of t notation. F of t is equal to the square root of 1 plus t squared. Exactly what I have in my integrand right here. And so my derivative of this in terms of x, finding the area under the curve until x, well, remember, f of t is going to be the same as g of x. I'm just going to take out my t and put in an x squared. You know what you're thinking, why didn't the bald guy just go ahead and just tell us this right off the bat? It's not too hard to go from this problem to this answer. And you're right, it's not. I'm just kind of over-taught it there for about, looks like 10 minutes to make sure you understand what's going on with it. Okay. All right, let's go again. I want to show you this other way that you'll see it in your practice problems. Again, it's going to say find the derivative of this integral. Now I'm here to tell you, that derivative and the integral undo each other. All right, they undo each other. Problem is, this time I have a function of x up here as my upper limit of integration. So I have a little bit of work to do. What I'm going to do is I'm going to let u equals x to the 4th. It's called a u substitution on it. Okay? And so I'm going to be able to rewrite this integral. I'm going to rewrite it as from 1 to u of secant t dt. Now I just can't randomly go around changing x to the 4th to u's. So I still have my d over dx right here in front. But I need to change some stuff since these guys don't match up. So I'm actually going to take the derivative with respect to u. 1 to u secant t dt, and then multiply the whole thing by du over dx. So I actually did not change the value of what I just previously wrote up here, because all I did was multiply by du over du. Okay? And I just moved this dx back here to the end. All right, so what does that mean for us? Well, remember, now these will cancel since I'm integrating with respect to the same variable here. All right, the differentiation and the integration are both the same, and I'm just going to have secant of u, and then times du over dx. Remember, u is equal to x to the fourth, so I'm going to dump it down right here. Secant of x to the fourth. And then du over dx is the derivative of u with respect to x. So the derivative of u with respect to x would be 4x cubed. And so I need to tag this on to the end of it. This was a little bit different because if you want to think about it this way, I'm trying to undo this differentiation, but there needs to be a chain rule that happens right here, kind of like an anti-chain rule, I guess, is I've got to set it up backwards so it still works. It's kind of a weird problem. I'm not going to hit that hard on it, as I don't think we'll see it very much going forward. Okay. Now, the more popular part of the fundamental theorem of calculus comes in part 2 right here. It says if f is a continuous function on a, b, then this integral from a to b that we've been seeing now for a couple weeks of a function is simply equal to capital F of b minus capital F of a, where f is an antiderivative. Remember antiderivatives back in chapter 4? Yeah, it's saying in order to figure out what this is equal to that we've been working with, all I have to do is simply take an antiderivative of the function. Let's see what that looks like. So I'm wanting to do the integral from 1 to 3 of e to the x dx. I feel like we've worked this problem already at some point in the last few days, but I'm going to work it again. And so in order to work this, I first of all want to make sure that my f of x, my integrand, is something that is continuous, e to the x. And then from there, I want to take the antiderivative of e to the x. So I'm doing it backwards. So what am I taking the derivative of in order to get e to the x? This one's a pretty basic one. I'm taking the antiderivative, or I'm taking the derivative of e to the x in order to get to e to the x. So in order to figure this out, all I have to do is plug in 3 into my antiderivative and plug in 1 into my antiderivative. I get e to the first minus, or e to the third minus e to the first, and whatever decimal that may count out to be. Or you can just leave it like this. That's an exact answer that I like. So we have a much easier way of solving these integrals now. Okay, now, the way that I just wrote it is not going to be the only way that you see it. You might see it a couple different ways. Now, I said what you'll see me do most of the time is I will rewrite my function as its antiderivative. So I'll go from the function to the antiderivative, and I will just evaluate it from a to b, so that my upper and lower limits of integration right here just come straight over. Sometimes you might get to a different calc class, and they rewrite it, and they just use a straight line. I don't use it that much, but that would be similar to it. Sometimes people don't like it whenever you just use half of a bracket. And so you'll see them rewrite the antiderivative, but they might put the whole thing in brackets. But I assure you all of these will be equivalent however you see them during your calculus careers. So I want to go back to the very first problem that we did back in 5.1. Of this chapter, we found the area under the parabola from 0 to 1. And parabola was x squared. Let me jog your memory on this. So we went just like so, and then we found the area from 0, I'll just call 1 right here. And we found that this area, using that big old long method, we found that it was 1/3, I remember. I'm saying now we have an easier way of doing this. Okay? To find that area, I can just do the integral from 0 to 1 of the function dx. And so all I have to do is take the antiderivative of this x squared, 1/3 x cubed, and then evaluate that from 0 to 1. So if I plug in 1 in for this x, I get 1 cubed is 1 times 1/3. If I plug 0 in for this x, everything zeroes out. This way is much quicker. I'm kind of glad you guys aren't in the room with me right now, because this is where a lot of people in the past have had tomatoes or fruits or vegetables and start throwing them at me, because it took us like 15 lines to work this problem earlier, and now we're able to do it in just 3 lines, 3 much easier lines. Let's get some more practice on this. Not going from 0 to a number this time. We're going from 3 to 6. Now, they wrote this kind of weird. I'm going to rewrite it so it makes a little bit more sense to me. 1 over x dx. Okay, that makes more sense to me. Or you can even say x to the negative first. And that would be fine as well. So, again, what we used to do was we had the reciprocal function, and we found the area under the curve from 3 to 6. We had all the approximating rectangles. Now, we can just use an antiderivative. So I want to take the antiderivative of 1 over x. Well, if I raise the exponent by 1, it gives me x to the 0, and put it over the new exponent, I get something really weird going on. But I urge you to remember that 1 over x was actually the natural log of x. Actually the natural log of the absolute value of x. And I can evaluate that from 3 to 6. So I get natural log of 6 minus the natural log of 3. And that'll simplify. I think the book will simplify it. Remember, if I have a quotient property here, I can do 6 divided by 3 and just get natural log of 2. Or you can feel free to decimal it out at any point from natural log of 6 minus natural log of 3. That'll give me the same thing as the natural log of 2. My calculator is kind of close right now. So let's go ahead and plug that in. 0.693. I'll gladly accept that answer as well. So whether it's asking for an integral or it's just asking to find the area of the curve, I really like how it hits both ways, because you're able to work them both the same way to two different questions. Okay? And so if it asks me to find the area under the cosine curve, that's just going to be my cosine x. Finding the area underneath it, it's going to be my integral. And it tells me that b is between 0 and pi over 2. We'll throw the dx on there. And remember, this dx is just taking the place of my delta x. It just means that my dx is just a little bit of x. It's just a very small width. Because ideally with this, I have an infinite number of rectangles. Okay. I'm going to let you work this one and then finish this off. And then you can hit play again and see if we match answers. So go ahead and hit pause, and then we'll work it out. All right, in an effort not to go back and rework the whole problem, I did misread this, and we actually are doing the curve from 0 to b. And this is just a domain restriction to make sure that whenever I do this, and I have all students take calculus, that I am staying in the first quadrant. And so I don't need that pi over 2 on this one. Rather, I'm just going to go to b on this one and do the antiderivative from cosine, which would be sine. I don't want that b yet. We go from 0 to b. So I can actually plug in a variable like this, and I have sine of b minus, well, sine of 0 is just 0, so my answer is just sine of b. That means that if I have my sine curve from 0 to pi over 2, which would be, I'm going to blow it up a little bit, about this much. If I'm just wanting to know what the area is until, say, pi over 3, because this right here would be pi over 2. So if I'm just wanting to know the area until pi over 3, then I can just take that pi over 3. I can take sine of pi over 3, which is square root of 3 over 2, and it would tell me that answer. Right? So it's just kind of leaving a generic answer for me on this one. All right, for real, I'm going to let you have this one. I want you to rework this problem, find the error that they have, and then work it correctly. Might not see it. Again, they went from -1 to 3. They plugged everything in. It looks good. But what triggered in my mind was that I got an answer to be negative, and I'm thinking about the graph of 1 over x squared, and everything for the graph under 1 over x squared is positive. So I would have no idea how to get down to the negatives. The kicker on this one is that it had a vertical asymptote right here. It is not a continuous function. And so I want to reemphasize to you guys, this is only going to work with continuous functions. And I can't find the area underneath an asymptote because actually the area of this just keeps going up forever and ever and ever. And it never ends. And so the answer, if I was to actually try to figure out what this is, the answer would be does not exist. Even though my fundamental theorem of calculus appears to work, I've got to realize that I don't have a continuous function there. Okay. Kept the video a little bit shorter this time. Homework should go a little bit quicker this time. I have questions from this homework set ready for the Q&A.